So welcome back to what will be my final lecture. I think Mark, I spoke to Mark earlier in the week and he said he would whip something up for you guys for tomorrow, but if not, you get the day off, I guess, because I've run out of material. So yeah, thanks for everyone for getting their assignments in. Might as well sort of start with that. So is everyone happy to, I suppose you've probably all seen each other's submissions anyway, more or less. No? Is everyone happy to show off their submissions? Sweet. So yeah, we'll just work our way down. So Robin's not here, so he can go first. So he's done Beast Wars Megatron. I happen to know a bit about Transformers, in case that wasn't sort of a giveaway. Yeah, so I looked through all your projects earlier, and it seems like you all got, pretty expectable results. Like, it was quite good in some ways, but other parts were falling apart. And I guess that is photogrammetry, really. If you, depending on how it goes, which way the wind's blowing and all these sorts of things, you might get good results. There's obviously things you can do, and I was glad to see most of you have sort of tried out a couple of things to, see how you could go. Yeah, so Robin started with Beast Wars Megatron, obviously did a few, at least 4 shoots by the looks of it, and ranked them. So this was his best one. He had a few books around, 45 photos. Looks pretty good from the front, but the back, by the looks of it, is a bit messed up. But to be honest, I don't think that actually looks too bad. The one he thought was going to be best has holes and parts of the background stuck to it. And then some other things as well. So he found that textures on the background weren't actually stitching, like when he put these textures underneath weren't actually stitching. And so it all sort of fell to pieces, which is not surprising. So I'll move to Mose. So you did a Go for Squishable, and it looks like you've actually done it on this machine because it appears that it's still there. And Autodesk has crashed by the looks of it. Which is,
I think I have a folder on the desktop.
Oh, okay. Oh, there you go. We can just click on it anyway. So yeah, how did you find it? Was it okay?
Actually, I also tried different. I did it multiple times, 3 times. One I took 99 pictures, but then it came out very bad. And then did another trial again, and that was the last one. So I did 3 different ones, and yeah, the first 2 were not as good as
the third one. Yeah, I mean that's it's the same thing with all the ones I did. In fact, you've seen the ones with the camel. It took, I think there's 3 things on there, but I think I actually did it 4 or 5 times. The other ones were just so rubbish that I threw them out. Still loading files. So how many photos did you use in the third attempt?
19.
19?
Yeah.
Oh, yes. Yeah. So, I mean, that's, I guess, one of the things I've found as well. There is a limit to how many photos sort of improve it, and then how many it starts sort of screwing up, if you have too many in there. So, whoops. Now, the user interface I find for this is pretty bad, but oh yeah, no, that looks pretty good.
Chuckles.
It looks a bit more angular than I'm guessing he is in real life, but yeah, no, that came out quite good. So you just used the one picture underneath it for texture, was it?
Yeah.
Yep. Sweet. Yeah, no, that looks pretty good. Morning. We've already covered you on, so we're just going over the assignment so far. So you had looked like you got some decent results in the end out of your last one. So look at Murray's now. So you did a Damascus knife in box. Yep. How many photos? I think you do say 25 shots, was it?
Yeah, no, it was about 20 around the bottom and about 10 above.
Yep. And so you, as I said, I briefly looked over these this morning. You're pretty happy with it from the front, but the back was a bit messed up.
Yeah. I didn't have a shot in directly like you're seeing from there on the right.
Yeah.
I saw that as the issue.
Yeah. I mean, it could have been, but I think you do say in here as well that part of the problem is potentially texture as well. So, yeah. I mean, especially things like the back of the box where you got the lid open and it's in shadow and stuff like that.
It looked like the tabletop.
Yeah, yeah. So there's
something white underneath it.
Yeah, I mean, it could have helped, or moded with his one, put a picture or something, so it's got some texture in there. You mentioned in there as well, you did a bit of manual point correction.
Oh, yeah, quite a bit.
Yeah, so we'll go over that a bit today because I didn't really cover that too much.
I've done it before because even with photo stitching that I do with the other type of stuff, there's always from time to time corrections to do.
Yeah, yeah. So I mean that's pretty standard of any computer vision approach. And then Jonathan's. So you did 2, and you actually tried out 123D Catch and Reconstruct Me, I understand.
Mm-hmm.
So you did 123D Catch on the watch, and again had mixed results.
Yeah, I was trying to do something like on a smaller scale to see how actually small objects.
Yep.
And also you mentioned last time that it has to be sort of non-uniform. So maybe the watch's band will protect the palms and so on.
Yeah. So when I said non-uniform, I was more referring to the texture rather than the shape of the object. So I mean the fact that the watch's band is all black probably didn't work so well. But I mean it looks like from the pictures anyway, it looks like you've managed to get most of the watch face sort of.
Yeah. Mixed results.
And
yeah, and then there was like errors.
yeah, I'm not sure. So Jonathan sort of asked me why I was getting so much errors with the service. I have no idea, but you eventually got it working on this machine, right?
Yeah, I just had to use this one.
And then you did one with Reconstruct Me, reconstructing Mo. And
Yeah.
so this is the mesh which it created, was it?
That's the mesh actually, because I did it by 3 or 4. I lost track of it.
That Mo?
Maybe 4 times.
He's in there somewhere.
But that's supposed to be like, that's Mary's disk, and that's my disk.
This is your desk and this is Murray's, is it?
Yeah, so what I did was I tried scanning the room. Originally the watch, I'm not sure if you can see it. It's,
There?
Yep. That was the watch and I couldn't pick it up, so then I should have saved the screenshot.
So where is Mo?
But I brought in the OBJ to try and see if it was usable, and then all of a sudden all these various popped up.
Right.
And I was like, that was
Yeah, so I don't know, like I haven't been particularly blown away, but I mean, I guess it's one of these things you just have to keep an eye on because they are still working on it. Like Connect Fusion was only sort of presented 3 years ago or something, so, you know, technique's getting better for the full version.
And there was another one that was expensive.
Oh,
Yeah.
that's good.
Yes, so, but I don't know that it's been nicely wrapped up into a package which you can use. Yeah. So yeah, I guess the results you guys got were sort of more or less what I expected. Like, you know, it was sort of mixed results. Some of them worked all right, some of them were a bit rough, but I mean that's the nature of it. But the fact of the matter is, unless your 3D modelers, it's probably, well, not all of us are. You know, it's probably not a bad place to start anyway. And even with the models, like, so for example, Murray's, you know, knife in the box with the back of that, you know, it's pretty easy. You start with that and then you can just import that into another 3D modeling tool and fix up the box by yourself. So you've hopefully you've saved yourself a little bit of work along the way. I guess one of the potential problems is the quality of the mesh which comes out of these as well. So when you're doing a 3D model mesh, you know, you can make it nice and clean and efficient and stuff, whereas this it usually just sort of does the best job it can. So you often find the meshes which come out of these are a bit rough, but never mind. So as I said, I just wanted to cover a couple of things, but I didn't have the software installed because I didn't expect us to get as far through as we did last time. So we'll just go through. Whoop, what's going on there? All right, I'm just going to reopen that again. So yeah, we'll just have a look at some of the ones. So this is the first camera one I did last time. So if you remember, there's the sign in. So if you're having problems with the software, as I found out, like if you want to export and you can't, it's because you actually need to sign in, which I think is a bit rude, but never mind. I suppose you get what you pay for, and that's how they make their money probably. But yeah, so I just wanted to show, did any of you other guys other than Murray have a go at manual point stuff? Yeah?
I'm sure I did it right. It made it a lot worse.
Yeah.
Mesh.
No, so in the 123D Catch,
I've done it before.
Oh, you can actually edit it.
you can do it manually.
It had a lot of stuff in it.
Yeah.
We just got to do a few. You need to do a few of them though.
Yeah. So what I'll do is I'll just run through a few of them at the moment, like to sort of show you guys how it works. So you can see here we've got a lot of pictures. What's going on? Why is that? What? All right. So we got some pictures which were able to be captured, and then a bunch which weren't. So you'll see all these. What is going on with the scroll bar? You can see here that of all the camera shots I took, and this has been particularly difficult today. Doesn't even want me to zoom anymore. Right. There's a way to... Like, only a few of them were able to work. So what we can actually do is we can actually stitch between images. So you see if we double click on one of these images down here, which doesn't have... which has these little warning signs on it, we can actually stitch it. And for ones like this, where it's got a yellow plus, it means there are features picked up, but not enough to do a match. So basically the way it works is we jump into our images like this, and we get given some images which have successful matches. So these are matches which have been picked up by, actually these are ones that I've put in earlier, I think. So these are basically successfully matched images, and then we have all our images which have no matches in it. So what we can actually do is we can go through and match the two of them manually. So let's start with, what's the lowest number we have? 3. So if I click on this one, so you'll see basically the matches that I've stitched here are on easily recognizable points. So if you actually click and drag, it's got this nice zoom interface. So you want to pick things like the corner of objects, intersections of objects, stuff like that. So we got one there, and what we can do is we can just go, all right, that point matches up to that point. This point matches up to this point. This one, so what was, this one's, there's a little dot on that book, which is that one there. And I can't actually do that one because I can't see that point. So let's just put in, let's put in another point. We'll do one at the intersection of those two lines. And that one there. And that is there on that one. So it says, you know, once you need a minimum of 4 points, and it'll say enough information being provided to locate this image in the project, blah, blah, blah. So once we've got that, it can basically say, okay, I know how these two images are related, and it needs at least 4 matches compared to 2 other images in order to be able to localize it. So then we hit submit, and it'll resubmit our scene for calculation and so on and so forth. So that takes a little while. So I actually did a few of these that we can sort of see along the process. So this is one now. So remember, this is having some problems rendering. So you remember in the first one we had 4 I think. There was 2 here and there was 2 over here. So you can see I've done a few more as well. And if we look at that, the 3D model now, it's starting to take a bit more shape. It's still, I haven't actually done any of the images from behind. But you know, you can see we're sort of starting to get a bit of flow for it. And then I ended up going through this whole process took me about half an hour or so. Whoops. This is the original one again. And this is the final one where I'd stitched all the images together by hand. And this is what I got out. So it's, I mean, it's still not a great 3D model, but you can see now we actually have 2 sides to the 3D model. We actually have a bit of shape and stuff like that. So you can actually, you know, do the stitching yourself if it doesn't work. Obviously, bad input equals bad output. So I just took a few images here, and it was pretty bad. And
Did you do every photo?
I did all the photos which missed for this one, yeah. So I think there was 13 photos in this collection, and you know, it's a lot better than it was, but it's still not really great. So does anyone have any questions about the stitching process? So it's really, I mean, what it's better for is if you have something where you've managed to get like most of the images, and so most of the images have successfully matched, but there might be 1 or 2 and a little bit of missing detail. So in something like that where, you know, probably 80% of the images were not successfully matched, it's not going to work very well. In this one here, I think all of these have been matched. But say, you can imagine if there was maybe one of these which wasn't matched, it might be worth doing there to be able to get a little bit better thing in it. So this is another one I did. So for some reason this time around, when I first did this, it didn't actually pick, like on the old version of 123D Catch, it didn't actually pick up, like you can see it's blended in some of the desktop background and stuff like that. The original version didn't have this so much, I'm not sure why. But anyway, let's sort of have a look at what we can do once we've got our 3D model like that. So obviously we've got our 3D model, we can zoom, like play through the animation path, which will just, you know, if you want to make a nice little YouTube video, it basically just interpolates between each of the photos, which is kind of cool. Let's just stop that. But let's say, okay, we've got this now. Now I want to actually get our 3D model out of it. Ooh. As I said, the interface for this is pretty wild. So what we can actually do, within the 123D Catch tool, we didn't actually used to be able to do this, but we can select portions of the mesh, we can delete chunks out, and so on and so forth. So we can actually like clean up the mesh in 123D Catch if we want. And now if I export this or whatever, so assuming I'm still signed in, I can export this capture. And you see here there's a bunch of different file formats, so Autodesk specific ones as well as OBJ, which is pretty industry standard supported, and so on and so forth. One other thing you'll notice when I first started selecting it, and if I actually open this one again, hopefully I've still got this data on here somewhere. So you'll notice if I first select something and hit delete, it gets us, before you edit your mesh, make sure you're working at the desired mesh resolution. If you request a different mesh resolution later, any edits you have made may be lost. It's one thing you can actually do is in the 123D Catch software as well, which I didn't talk about earlier because I just wanted you guys to have a play and not worry about the fiddly bits, is you can, in the toolbar, you can actually click on Generate Mesh. And you see here you can choose output quality, so you can pick mobile, which is a low resolution mesh, standard, which is what you normally get, and maximum, which is a high density mesh. And obviously, so for example, Mo, with your one of the thing I sort of mentioned when we were looking at it, that it looked quite angular and stuff like that. So you might find if you go to a maximum density mesh, you might actually find that it ends up a little bit smoother. Obviously that depends as well on how well the capture happened and so on and so forth. Let's have a look. The thing is, though, that when you change between the meshes, it actually has to do all the processing again on the server and then download it all. So it's not like a magic, you click the button and then it's done. Maybe I didn't. So I did actually have a look at it. And so for the robot, for example, oh, here we go. No, I did it for the camel. I did actually do it for one of these. Oop. So let's have a look at the difference. So here we have a standard mesh and a high-res mesh. So I did this for the camera one. So this would be a good example where image stitching might be useful. You can see we've got most of the images have actually loaded through. We've got a few ones which didn't quite get there though. So we might choose to stitch these images manually just to try and get that extra little bit of data. I haven't actually bothered in this, but so this is our camel, and if we have a look at it, you know, it actually doesn't look too bad, but there are a few sort of rough edges and stuff like that in there. Down here it's sort of like straight line and so on and so forth. We'll open the high-res capture as well.
Changing mesh resolution doesn't require going to the server again.
Yeah, so it actually, the server will do, you don't have to upload all the images again, but the server will reprocess it to generate a higher resolution mesh and then download it again. That's why I did it beforehand, because I found last time, when I actually did this, you know, to generate a new higher resolution mesh, I think took about 15 minutes or something. So, so this is the higher resolution mesh, and you can see it's actually in some ways looks kind of worse. So, you know, it's picked up some of these errors, which errors in the photogrammetry have actually carried through now. So you can see here we have this weird little fur flick out the front now, which shouldn't be there. So there's no guarantees that the high resolution mesh is going to be necessarily any better. It just means there's more polygons in there. So, you know, errors in the photographs that you've taken or errors in the stitching might actually end up with a higher resolution mesh, which is worse quality than your standard resolution, because it's trying to model all of those, whereas a standard it just sort of blends them out. So, you know, it's one of those things which is worth maybe having a bit of a play with to sort of see what you end up doing or what you end up with. So just bear with me, because I had this all set up, but then they had to do a demo yesterday, which Actually, hold on. So that's not ideal. Oh no, there it is. Sorry. Right. So OpenSceneGraph is something I think I briefly spoke about when we were looking at graphics, but it's basically a 3D. It's a 3D graphics library built on top of OpenGL, which supports scene graphs and stuff like that. It also has a bunch of plugins as well, and it comes with this OSG viewer, which can load OBJ files. So you saw before we had an OBJ. We could create OBJs. So this is basically when we have it in this format. This is being loaded and rendered into OpenSceneGraph. OpenSceneGraph you can write your own games and everything with. So we can see now from 123D Catch we can actually get our models into a format. We could now use them in games or whatever, games, visualization software and so on and so forth. The reason I wanted to sort of show you this is because it has nice lighting on it, so we can sort of see, you know, when I had a look I thought it sort of illustrated the differences a wee bit better. So this is the standard resolution one, so it doesn't actually look too bad. And now if we do the high res, so it takes a wee while longer to load because the high res model is a larger like file size and everything.
You will rotate the model with respect to the light.
I don't know that the light source was moving. Yeah, I don't think that it can, but so
Made in China, but
yeah, I know. I was actually quite impressed that it was able to pick up that resolution. So yes, my little software camera was made in China, but you can sort of see the difference between them. So in the last one, it was quite sort of smooth, whereas here it's all like dimpled and lumpy because it's done its, you know, the mesh has been less smoothed out, I guess, to try and make it lower resolution. So depending on what you're actually trying to capture, in this case it's picked up a lot of textures which probably weren't really there, but you can sort of see around here there's all these little lumpy bits and stuff like that which weren't there in the standard model because they get smoothed out. But yeah, from here we can import it anyway. And also we'll just have a quick look at Mesh Mixer. So Mesh Mixer from memory can also import OBJ files. So you know, if you want to use Mesh Mixer, you can export to OBJ. Just remembering that you have to sign in order to do it. It took me about 10 minutes to figure out because I was signed in initially and then it signed me out for some reason. I couldn't figure out why I wasn't allowed to do it anymore. But Mesh Mixer, and we'll have a look at this again in a minute, we can import it, and this one has a pretty weird interface as well for, yeah. So Mesh Mixer can import stuff. Supposedly it can import textured models as well, but I wasn't actually able to get it to do it. But so this is the robot one, and we can do all our things we did before as well. So we can, they have this weird selection tool where you can select, I think it's, if you select one way, it's everything you've selected and including the line as well. If you select the other way, it's exclusive for the line or something. So, but what's probably easier is if you just go to, oh, sorry, that's right. So you just try and click and drag everything you can, but you'll also see, like you'd think if you use the mouse wheel to scroll in and scroll out, it would zoom. It actually doesn't. You can see I've got this little spotlight thing which changes size as I move the scroll wheel, and this is sort of like a painting selection tool, so we can actually select surfaces by painting on them. There was one other thing, I think on...
how would you fill in a hole?
We'll get to that. I'm glad you asked, but we'll get to that in a few minutes. So if I open... There's one other thing that I came across in the last one. So depending on your mesh, so this is one I did for last year's group. So basically the controls are middle mouse button is used for rotating, and if you want to zoom, it's actually hold down shift and use mouse wheel, and if you hold down shift and click and drag, it pans. So mouse wheel or middle mouse button is rotate, shift to middle mouse button is pan, and Shift and scroll wheel is zoom. I don't know why, incredibly unintuitive, but never mind. But yeah, so if we look at this, this actually isn't the one I wanted to select. But if you end up with this sort of situation, all right, where sometimes you have a mesh and you can't, so for some reason I must have accidentally saved over this mesh, but like sometimes this old mesh used to have all these bits, and if you tried to select them, it wouldn't actually select anything. If you see this object browser window pop up, it's because you have multiple objects in your window, and it's possible that you're on the wrong mesh to select the object. So what you want to do is if you click on the little eye thing there, you can see it actually hides one of them. So you see here I have two meshes. One is responsible for like a tiny little bit of mesh around, mainly on the base. In fact, it's these weird sort of things around there, whereas the other one actually holds pretty much everything else. So if you're trying to delete stuff in Mesh Mixer and you're finding that you can't actually select anything, make sure you use the right mesh, and what we can actually do is just delete that mesh, and then we can work on this one as we would. So we'll come back to Mesh Mixer a little bit later on in the class, but does anyone have any sort of questions about those two tools? As I said, they're not necessarily the best tools, but they're out there, they work, and they're pretty easy to use once you get past the weird user interface stuff. Right, so we've sort of looked at various ways using self-modeling, using photogrammetry tools like 123D Catch, using laser scanning, using Connect-based stuff, and none of them are perfect, but they all sort of have strengths and weaknesses. And you can sort of set up a workflow that you could grab it. You can imagine grabbing a model and then sort of cleaning it up yourself in Maya or whatever, if that's what you need to do. So that's sort of one sort of path, going from atoms where we have physical objects and then scanning them so we can bring them into the computer. So the other part of that was basically going from this this representation within a computer to a physical object. So we went from atoms to bits, and now we're going from bits to atoms. So obviously, the ideal, the dream goal would be the replicator on Star Trek, where you define something and somehow I don't know, I'm not a Trekkie, but maybe if any of you guys are, you can explain the pseudoscience behind it, but pulling in atoms to create a physical object from, there you go, someone's a Trekkie, from creating physical objects from an idea or some sort of physical thought. So there are technologies which can do this to an extent, and obviously the main one, and what we're going to be talking about more or less for the rest of this lecture, is 3D printing. So 3D printing is kind of a pretty generic term, which actually has sort of evolved from the specific term into a larger encompassing sort of thing. So 3D printing, as it's defined these days, is basically a sort of a collection of tools for creating 3D objects from some sort of physical material. Originally, 3D printing was defined as a tool which works in a similar way to an actual printer. So it has like some sort of cartridge or source of a material that it lays down, like when you're printing ink. So that was like this 3D digital printing technology there. And then in separate, we also have StereoLitography, and we're going to look at these all in a minute. But StereoLitography, which uses lasers to harden a resin in a vat, and fused deposition modeling, which is what 3D printing, most 3D printers you buy these days actually use fused deposition modeling. But you can sort of see the technology's been around for ages. So this is a StereoLitography machine from 1984. Right up to 3D digital printing technology, which is sort of around early 90s. So this technology isn't really new. The reason there's been a big push in it lately is because it's finally become affordable for home consumers to use. So as I said, there's different types of model creation. They all sort of fall under, all of these ones fall under the idea of additive fabrication. So obviously there's additive fabrication, there's subtractive fabrication. So additive fabrication, you start with nothing and you begin putting layers and layers and layers down to build up something. So you can imagine the idea of making something from making a clay coil pot. So you start with nothing and then you build up. Obviously, the alternative is you start with subtractive fabrication, where you start with a block of something and you carve it out. So that's, what's it called? Like CNC routing and stuff like that, where you start with a solid block of, or milling, you know, block of aluminium, and you have these things which go through and drill it out, or you can do it with wood and all this sort of stuff. But we're going to mainly look at additive fabrication because this is sort of the way, this is the more popular technique. And we have a 3D printer in the lab, so it makes it nice and easy. So yeah, 3D printing, as I said, the more specific, I mean, I'd argue that it's more correct, but language is an ever-evolving thing, so whatever, you know, I'm a firm believer in that anyway. I know people will argue with me, but I believe that language is an evolving thing, so whatever people are defining 3D printing as is the definition of 3D printing, but the older, more technical term is an object which is made up using inkjet technology in 3D, so you have a device which works in a similar way as a inkjet printer, except instead of printing out ink, it's printing out some sort of matter. We have fused deposition modeling, which is what most things work, simply because the technology is pretty straightforward. It's pretty easy to use. Where we have some sort of plastic material which is melted, and then we draw it out like if you were doing with it's basically a hot glue gun, except it's run by a computer. StereoLitography, which is where UV light beam is shone into a photosensitive pool of liquid. And selective laser sintering, which is where a laser is used to basically melt a powdered base. So the difference between these two is stereolithography basically hardens a liquid, whereas selective laser sintering basically melts a powdered base. Yeah, so 3D printing, it uses inkjet technology in 3 dimensions by layering powder and binding it with pigmented glue. So that's not what we think when most people talk about 3D printing. They're talking about fused deposition modeling, but the original definition, it lays down powder and then glues it together. Fused deposition modeling is the more common one, where we melt some sort of plastic or whatever and then layer it layer by layer. Yeah, so a bit more into that because this hasn't really ever sort of taken off in a commercial or in a consumer way anyway. So fused deposition modeling based on CNC, so computer numerical control, and we have a 3-axis robotic print head. So depending on how it works, usually the 3 axes are you have 2 axes on the print head, and then the last axis raises and lowers the printing body. There are other ways of doing this as well. So you have the DeltaBot style, where you have the printing head and it's connected. Actually, it's probably easier to show you a video. DeltaBot 3D printer. So this is sort of more like a robotic arm. So you have these 3 robotic arms which sort of control this thing. And, you know, there are different advantages to doing it in different ways. So this actually allows you to do sort of more intricate designs, really, because in addition to position, like rotating, moving the arm around, you can actually rotate the arm as well at the head. So instead of just being forced to constantly print down, you can actually print around the side of structures. So if we can do, depends on which one you do. So RepRap has its own 3D printer, you know, a couple of $100, maybe to a few $100. So this is a robotic delta printer, so it basically calibrates it because it's printing in a 3D plane. You see it come in and it calibrates the 3D plane so it knows what to print off. And, you know, they sort of wobble around and they do their own stuff. One of the downsides of this over the standard 2-axis CNC style head is that it, you know, because you've got 3 moving axes here, you often end up with like looser tolerances. It's easy to control something which moves out and across rather than 3 things which are moving up and down at one point in time. So you might find that models in this models in this format have lower tolerances than what you'd have in your standard 2 axes. So, you know, there's plenty of, I don't really want to listen to some guy talk about stuff, but I'm trying to find videos of them actually working. So they are quite cool to sort of watch go, but yeah, they haven't proved to be as popular simply because they can be a bit harder to go. But those are the sort of 2 main things for fused deposition modeling. And then you have the extruder, which comprises of a feeder, so it basically pulls in the filament, a heated barrel, which heats up the filament and melts it, and then the nozzle, which squirts out it in a nice fine tube. So yeah, these are 3 parts. Filament comes in, the feeder basically pulls it in, often it's just as simple as a couple of wheels which grip into the filament and slowly wind it in, a liquefier or the heater, and then the tip, which basically squirts it out in a nice thin thing. Pretty simple technology, really. But you can do, this is basically the process. So you start with a 3D model. Your 3D model comes into what's known as G-code, which basically specifies, this is set the temperature to 220 degrees Celsius, so on and so forth. And then it's like move the thing to here, and then follow this axis around. It 3D prints it, and you end up with your 3D model. StereoLitography, I mentioned, is where it traces a beam of UV light over the photosensitive pool of liquid, and then it basically draws it on the top, and then it sort of moves down. So instead of moving up like a 3D printer lifts the print head like this, StereoLitography shines lasers down, and then it gradually lowers the part in. So it's only ever sort of firing at the top. So here's, you have your laser and your scanner system, which bounces the laser back and forward, and then it basically hardens the resin, and then the resin sticks to whatever's below it, and then the platform gradually lowers it in. So StereoLitography was originally sort of, it didn't take off as fast, but there is the recently, like late last year, I think it was, there was the $100 3D printer Kickstarter. See if I can, PT printer, that's what it was called. So this guy came up with this idea to develop this 3D printer for $100, and it uses StereoLitography. So kind of a clever idea. The video is quite boring. It's this guy who is personally, I think, not the best sort of spokesman, but so what basically, he's invented this quite cool idea, and basically it uses your computer sound card, because your computer sound card has 16-bit accuracy, to move a couple of mirrors, and then it shines a laser into it, and it has this. It's pretty clever. I have to give him a lot of credit. He's built this pretty clever machine. He uses a computer sound card to control the mirrors, which shine the beam. Looks like he's about to fall asleep most of the way through the video, and then it has this drip feeder which feeds the resin in at a rate such that instead of the thing lowering into the solution like we just saw in this thing, the liquid actually gradually fills up, and it shines the laser in to harden it. Because it uses pretty simple stuff like a very simple drip feeding thing to shine in the resin, and little mirrors controlled by your sound card. He was able to build it for $100 out of his own thing. Aimed for $50,000, raised $651,000. So, he did really well for himself. So kudos to him. But yeah, he did a good job. And you can. I'm not quite sure how far this has come along. It's been a while since I had a look, but I think they started shipping it out, and you can print out things with your Selective laser sintering $100 sub $100 3D printer, which is quite cool. And one of the other great things about it is it's really small. So you guys have seen the 3D printer in there. We've got it's yay by yay. This one I think more or less sort of fits within the palm. Like you can carry it, folds down, fits in with the palm of your hand. There are images of it somewhere.
So hooks into your computer.
Yeah, so it plugs into your computer. So unlike the RepRap we have, which is there we go. So there's the device next to what looks like a EEE PC. So one of the netbooks. So what's it? I'm not actually sure. You have to follow up. I think. Yeah, I don't know. It must be pretty close, if not already there. But yeah, you can see, so this is one of your netbooks, so one of those tiny little laptops. And these parts, it's telescoping thing, so it actually all folds down to be quite compact. So really cool idea, obviously hugely popular. Wait to see what comes out of the Kickstarter, because this is the prototype. We can see is rubber banded things together, and there's like stuff hot glued together. So, it was pretty rough, and the 3D print sort of reflected that. But one of the things they're aiming to do with the the Kickstarter funding was to basically make it a lot more accurate and stuff like that. But yeah, as you were saying, hooks into your computer at the moment. But you can imagine with something like Arduino, Raspberry Pi, you could have it automated. Anyway, after that long aside, I just thought I'd show you because I thought it was quite cool. So yeah, StereoLitography, there is stuff coming out, like 3D printers coming out there, which you can buy. Selective laser sintering is sort of the last main technology style which does it, which is where you use these pretty much same technology, except it burns this powder and the powder melts together to form this thing. One of the advantages over doing selective laser sintering over fused deposition modeling and stereolithography is if you imagine printing out something like which sort of expands as it gets wider, fused deposition modeling, it prints it to the layer below it. So you have nothing coming out. So as it starts warping, like moving outwards, these layers have nothing to hold on to. So as you start printing it, it'll all start drooping like a flower. So you end up with having to do something like this scaffolding you can see, and we'll talk about this a bit more in future, but you end up having to print all these scaffolds, which then you have to remove, and it becomes a real pain. With stereolithography, it's the same thing because we're printing on a floating resin. Any parts, overhanging parts we print, unless they're like close enough together, will need some sort of scaffolding, otherwise they just fall into the thing. Because selective laser sintering is printing into an existing 3D medium, we don't need to worry about any of that scaffolding because these parts we're printing up here, we have this overlap is supported by all this powder which is sitting in there anyway, so it has that that benefit. And the other thing we can obviously do is, like this one hasn't been particularly popular, but things like laminated object manufacturing, we're basically sticking stuff and it cuts it out and then glues it together. So we have glued like thousands of sheets of material to form solids, sometimes with stand A4 paper. So, there are other ways of doing it, but you're not likely to come across them apart from in very specialized sort of environments. So yeah, as I said, these technologies have been around since the 80s, and it's only sort of been in the last 5 years, 10 years maybe, that it's become really popular, and that's because we've had this move from commercial to home. So yeah, rapid prototyping machines have become compact and available at semi-affordable price points, allowing in-house fabrication capabilities for enterprises such as industrial designers, small-run manufacturers, research labs. So, we've sort of gone from this thing where, they're in the tens, or, this is probably still somewhat affordable for a large design factory, $30,000, but, before that we're getting down to, $15,000, which isn't a huge expenditure for a company to buy it. However, it still puts it out of the realms of the accessibility of most home hobbyists. So, I'm not going to go put down, you get getting towards a deposit on a house or at least a very nice car for a 3D printer.
Sorry.
That's right.
Like people that print out like plastics, like what do they use?
So we're getting to that. So I mean, like for the if it's something like this would be injection molded or something if you're doing a large run. But if you're prototyping this in a like a development thing, they probably would have something like one of these machines here. So because these ones are just highly accurate, they're highly stable, and so on and so forth. So if you're doing it yourself, though, with the sort of there was all open source software has been around for decades, and gradually sort of technology caught up, or hardware technology sort of caught up, that we started getting things like the Arduino, the Raspberry Pi, and all this sort of stuff, which opened up this open hardware platform for people to start working with as well. So, these things made it a lot easier to start working with hardware, and from that people were like, well, this 3D printer technology is really cool, why can't we make our own one? And this is what they sort of arrived at. So you can see here, this is pretty prototypey. This is actually a CNC mill, so you'll see it's actually got like a little drill bit in there and it's used for cutting it out. But CNC mills and 3D printers are very similar technology. So you have this two-axis thing that moves. You can see you've got some rails here, so its whole gantry moves back and forward, and then you've got another rail here which moves this from side to side. And basically the difference between a 3D printer and a CNC mill in this respect is you just replace, here they have a drill, you replace that with an extruder, and you can do one from the other. Obviously this only works in 2 dimension. This part may move up and down, I'm not 100% sure, but there's less emphasis on this having that third dimension, which we do want in 3D printing. So there might be a little bit more work adding a Z-axis as well if you want to do it. But this one, as I said, I'm not 100% sure about this specifically, but this may actually move up and down, which would give us a little bit of Z-axis as well. But yeah, so people were sort of building these things out of hardware you can buy from various hobby shops or hardware stores, and starting to build their own things together. And from that, one of the first ones which sort of came out in the 3D printing scene was the RepRap. And from memory, RepRap stands for reproducible replicator or something to that extent. And the idea was that it is a 3D printer which prints its own components. And there was sort of this was all open hardware design, so they put the plans and everything out there. So obviously in this case, it's just all the joining pieces, all of these metal rods and print platform and electronics and stuff you still had to go out and buy. But the idea was there was a sort of this community thing that when the first thing you print out on your 3D printer was components for another 3D printer that you passed on to the next person. So you have this sort of chain where you get the parts from someone else, you print out some parts and pass it on. So there's this constant self-perpetuating cycle of people building 3D printers, which is kind of a neat idea. But obviously in this case, it's only sort of, but more legal at the moment. Oh, there we go. Replicating rapid prototyper. So you can sort of see all these, you've got all these bars and stuff, but all these connecting pieces, you go out to the store and you buy a bunch of rods and then some threaded rods, and then you have to buy various components as well. But all these connecting components you buy from someone else who has printed them on their device, and then you print some else and sell them or give them on or whatever. So there's been numerous iterations of these RepRaps going on throughout time. So we had, these sort of cuboid-based ones. Then we had this one, which is sort of more like a pyramid, and so on and so forth. And lots of different iterations. But that while that's all well and good, if you don't know what you're doing, you're kind of not going to be able to build this. We had a student here. I think he built a RepRap, and it took him dozens of hours to put it together himself. He was always constantly trying to troubleshoot problems it was having with it, and he would get it working, and then someone would bump it, and he'd have to go and recalibrate the whole thing, because then the printing platform would be slightly off skew, and it was a lot of trouble getting it up and running. And other people noticed this. So Bree Pettis, the MakerBot co-founder, said around the RepRap that it's still not trivial to put a RepRap together. It requires a lot of enthusiasm, a healthy dose of bravery, and the ability to navigate a project that is growing and changing every day. There aren't step-by-step instructions which make it a very challenging project. And this is true of a lot of open source sort of stuff. If you guys have ever tried to work with open source software, often you'll find 1 million people have contributed to it. Each have done their own thing. The project is sort of partly documented. You try and sort of get it working, and there's some key steps which have been missed out in the process of getting it together. I'm not trying to knock open source software here, because I love it. I think it's great, but there is a huge difference between good open source software and the rest, where the rest you pick it up and you spend more time getting it up and running than it probably would have taken you to write it yourself. So, and it was the same thing with these RepRaps. It's a system, especially early on, they're evolving so quickly that everyone sort of puts out their new iteration, and they sort of roughly document it, because let's face it, the fun thing is building these things. It's not then writing on the internet about how you built these things, taking lots of photos and doing lots of instructions and answering lots of questions about it. So you had this sort of thing where if you really had the time and energy to devote to reading thousands of pages on how people built it, the challenges they faced and how they fixed them, it's a pretty overwhelming project. So MakerBot was like, all right, let's try and sort of standardize this a bit more, and release these kits. So building on the intellectual and physical resources born of RepRap, a team of New York City hackers started MakerBot Industries, a company that manufactured and markets affordable 3D printer kits. Some assembly required. Well, that's depending on which ones you do these days. Earlier on, there was some assembly required, but it was DIY light. So in these ones, you go to a hardware store with a list of materials, and you hope that they have it in stock. If not, you drive around to another one. With MakerBot, you buy it, and it comes like an IKEA kit set sort of thing. So you just assemble it yourself and hope that all the pieces are in there. So this is their first one, I think, or one of their very early ones, which I think was called the Cupcake CNC printer. There you go. And it has the same sort of stuff. A few more minutes, then we'll have a break. Laser cut wood frame, extruder head, XYZ axis, plastic filament, all the bits and pieces that the other ones had. But you buy it, and everything's there ready for you to go. So this is the model. If you want to, I guess you could, like, being that it's open hardware, you could download it yourself, and if you've got a CNC printer or CNC cutter or whatever, laser cutter, you can print it out yourself. Otherwise, you can buy a kit which has all the bits and pieces included. Here is the extruder that you buy, which comes with the circuit boards and everything, and heated filament, so on and so forth, and all the electronics which go into it. So you buy it as a kit and then assemble it rather than trying to source all the pieces yourself, and filament, and you can print out. So because it was the Cupcake printer, like their sort of giveaway 3D model that they had was a cupcake with the MakerBot M on it, and so on and so forth. So the Cupcake scene, this is a while ago now, but we can go to the website now and see how far things have come.
Is it the case that by the printer, but you're still paying for the ink?
Yeah, so we'll look at filaments and stuff in a minute, but yeah, there are different approaches at that. So this is the old store, Cupcake CNC Deluxe, pretty professional looking device made out of bits of plywood and stuff. $950. This is the current MakerBot website. So the MakerBot Replicator Mini looks to be their most basic one. Yeah. So they've really sort of taken it to the next level of, pretty professional looking stuff. The 3D printer we have is a MakerBot. Prices it's a little bit more expensive, but it's still within the realms that if you're really keen on this sort of stuff, you can get one. This one?
No, the very last one.
The digitizer?
Yeah. I just have a look at that.
Yeah. So the digitizer isn't actually a 3D printer. This was an add-on that they released, I think, sometime last year, which is basically a 3D, uses lasers and a camera to do a low-cost laser scanning of 3D objects. And it's designed to interface with their printers. So you put an object on it. This is a little turnstile, turns around, projects lasers on it, uses the camera to pick up where the lasers are, build a 3D model of it, and then you can print it. So it is essentially, if you think of this like a printer, like a regular printer, this is the photocopying scanning mechanism.
So you said before in the past they're very
$900, $1,000.
It's the top of the line model.
Without, yeah, okay, yeah. So it's $750. So that one, we'll open up these two ones because I'm not actually sure what the Replicator 2X is. It might be the double extruder.
just bigger size, or is it different?
So this one has dual extrusion. So we'll get into dual extrusion a bit. So $2,500 or $2,000 if you want the single extruder head. Yeah, yeah. So I mean, they're still expensive-ish, but if you think of a top of the line computer is going to run you about that sort of money as well. So if you have the choice between buying
$5,000 for a custom built computer.
Sorry.
Out of $5K for a
Yeah.
custom built.
Yeah. So I mean, if you're thinking about a custom built top of the range computer or a 3D printer, you're looking at the same sort of thing compared to the $25,000 it was. Though these are the good thing about the MakerBot devices are they are mass produced. So there are sort of certain tolerances and all these sorts of things. So you're not even with our MakerBot, we still spend a lot of time trying to maintain it. But it's certainly less time than if you built it yourself or anything like that.
Oh, there's one down there.
Sorry.
Do we have a MakerBot?
Yep. So we have this one actually, the MakerBot Replicator 2.
Oh, wow.
Marketing photo.
Yeah. No, I think I mean, there might be slight revisions to the design of it, but it's the same sort of technology. Yeah. So that was the MakerBot. We have a MakerBot Replicator. Replicator 2, one or the other. Yeah, this is the older models. Then there's other ones as well, obviously. So there's the Fab at Home Faber Model I. They've probably got new ones out as well. I haven't actually checked on these guys in a while, but all these different 3D printers offer different things. Let's move that over there. So the printers, what have these guys got now? Model 1 and they've got a Model 2 out now. But the thing that the Fab at Home guys did is they tried to move away from this sort of fused deposition modeling type thing using ABS filaments and stuff like that. And instead they use a syringe type thing, which is kind of cool because it allows you to print with a bunch of different things like silicon, cement, stainless steel, cake frosting, cheese. If you can stick it in a syringe and get it liquefied enough to squirt it out, the Fab at Home will print it. So yeah, depending on what you want to print.
What do you prefer?
It depends on if you want to be able to make it edible, I would recommend not using ABS plastic. But yeah, it depends on what you want to achieve with what you're doing. Yeah, well, I think it's non. Yeah, well, yeah. So PLA is non-toxic, is it?
ABS melts.
Well, I don't know. Yeah, I was going to say I don't know that you could eat PLA, but even if it was edible, I wouldn't recommend it because it's still plastic. Well, it still has that plastic. So if you really want to print out of something you can eat, maybe you want to go for the Candy Fab. So the Candy Fab is the revolutionary. Well, the revolution will be caramelized, and this is a 3D printer which prints in sugar, and can do a variety of other low melting point materials. So you can make huge, big 3D printed stuff out of sugar. Would you want to? Don't know.
Going for lunch and
Yeah.
It's like pure sugar.
Yeah.
It's like death.
And it's probably being caramelized. It's probably teeth shattering as well if you try and eat it. But never mind. The options are there. You know, that's what I'm trying to get to. But so you know, it's only $500. The Fab at Home is $2,300. These are around the $1,000 to $2,000 mark. So there are options out there depending on what you want to do.
sugar.
What's that?
Only sugar, nothing else.
Yeah, as far as I'm aware, just heats it up into caramel and prints it out. But yeah, there's lots of evolutions going on. Obviously, there's all these different ways of printing stuff. The most recent sort of news announcement that I'm aware of, this was a couple of months ago. They're talking about new 3D printing technologies, which are printing in carbon fiber. So obviously, carbon fiber allows strengthening in certain ways. People were talking about it as the be-all and end-all. It's not quite true. You know, the carbon fiber still has its limitations, but the idea was because carbon fiber works on the strength of the fibers, so you can't just melt it and print it out because that's not what carbon fiber is. So you basically print your 3D model, and then you'd have like another head which was printing the fibers within the sort of stuff. So it adds a certain amount of strength in certain ways, I think, flexion, but
Putting layers of carbon fiber. So what do you do? Like the base, the carbon fiber against the strings.
yeah, but it needs to be one sort of continuous strand, so you can't do a layer of carbon fiber and then a layer of carbon fiber because they would just peel apart like paper.
So you do a layer of plastic, then a layer of fiber, then a layer of plastic.
Well, you'd print the carbon fiber within the plastic most likely as one continuous strand. Yeah, because if you printed layer upon layer upon layer, you could probably just peel it apart like corrugated cardboard. So the trick is to print the carbon fiber in it in such a way that it retains that structural integrity. Yeah, and there's other things as well. So there's technologies towards printing in various materials like metal and stuff like that. Anyway, obviously evolving output quality. So, you know, €400. This is from a while ago anyway, 2008. But you know, the technology is getting a lot better. I saw something on Hackaday yesterday where somebody had changed, just by changing the software and the extrusion rate on a standard RepRap printer, they were able to get much better prints. So $400 RepRap printer versus a €20,000. See, this is a little bit cleaner, you know, and these sorts of things going on. So early on, you know, I think that was actually a drilled out hole, so it was a solid thing. And then as time's gone on, the print quality has gotten higher and higher. The resolution's gotten better and better. The resolution they're claiming with that $100 Peach printer is supposed to be like an order of magnitude better than the fused deposition modeling, because all you're using is a laser as the print head resolution rather than the print head of the nozzle and the thing and everything else.
Anything going on in the biological area?
Yep, plenty actually. So Not a week goes by that they don't talk about like 3D printing for biology. They've done a lot of stuff with printing out these dissolvable biological filaments, so you can print out a 3D heart, dunk it in a thing of stem cells with some heart cells, and it will basically acts as the scaffolding, and then over time it dissolves. So yeah, plenty of stuff going on in biology. Actually, we'll have a break in a minute and I'll go down. I actually have some more recent slides for another talk which talks about future directions. But yeah, biology, lots of stuff going on in various materials, so metals and stuff like that, because obviously metal is a lot more durable than this sort of stuff, which is still quite, flimsy. Yeah, and so on and so forth. But I will take that as a chance to have a break, so if you guys want to go to the bathroom or anything, do it now. Oh, yes. So yeah, there's... All right, so let's get back into it and knock this out. There we go. All right, so just wanted to sort of briefly touch on a couple more things. So as Mo sort of mentioned just after we finished, there's been this thing lately on 3D printers which can print houses. Supposedly there's this printer which can print a house in 20 hours, which isn't too bad, as long as you like your houses as cubes.
Oh, there's some sort of
Yeah.
There's some sort of
Art Deco.
Art Deco, is it?
Yeah. Well, yeah, I mean, obviously it's just a matter of time before these things sort of become better, really. Oh, yeah. But was it worth would you live in it though?
If you wanted to with more.
Yeah. And as Murray was sort of saying, there's obviously a lot of interest in using 3D printers as printable organs. So producing stuff about like being able to print scaffolds for cell structures.
Replace your liver.
Yeah, yeah. I mean, the liver's self-regenerating, so it's potentially less useful, but unless you've got a disease, but like kidneys, hearts, stuff like that, you can get a cell culture and then breed it, multiply it, dip your new organ, scaffold, your kidney, whatever in there, and then they will basically, the cells basically fuse to it, and then you've got your own kidney, which was printed from your own cells, so there's no fear of rejection or anything like that. Okay, I haven't actually seen skin graft stuff, but it certainly makes sense anyway. Yeah, so just a few applications. So 3D printed facial reconstructions. This guy, I think he had cancer and got a bunch of his face removed, so they 3D printed it based on they created a 3D model of his face and mirrored it and I guess tweaked it a little bit. So I mean, it's still not perfect, but compared to what I guess is under there, it's probably a lot nice to look at. Obviously, there's all the art and stuff like that. This one was from a guy in New Zealand at Victoria Uni. Got a lot of publicity when this happened. So a cast for when you break your limb. So it's breathable. You can scratch yourself without having to try and jam a ruler or anything down there. And I actually saw an article just earlier this week which was talking about these again and how one of the potential benefits is there is evidence which shows that ultrasonic vibrations can aid in bone repair somehow. I don't know. But they never use it because the ultrasonic vibrations get absorbed by the cast, whereas if you had something like this, obviously you can actually poke through the holes and do it. This is something which has got a lot of publicity, not so much this year, but certainly like last year and the year prior. So because America, a bunch of guys set out to create a functional 3D printed firearm, which they were successful to do. Across multiple iterations, they were printing out various stocks and bits and pieces of firearms, but they actually created, in the end, the Liberator, a fully 3D printed gun which is capable of firing a bullet. Ethical ramifications, obviously. A lot of bad publicity for 3D printing. A lot of, you know, politicians and stuff getting very concerned that people are going to start printing out their own 3D guns, which are untrackable and cause a revolution. Thing is, you can actually go down to a hardware store and buy enough components to build your own gun for cheaper and easier, but that's neither here nor there. And obviously, things like quadcopters and other technologies as well are benefiting from this a lot. So challenges and solutions in 3D printing. So there's things like the cost of print materials, as Murray was talking about. There's pretty much a 10-time markup in that. So the PLA and ABS plastics that you get, you can buy the raw pellets, like just little pellets, for about $5 US a kg. If you're buying the plastic filament, it costs about $50 a kg. So someone has taken the time to melt it down and extrude it into a long filament, and they charge you 10 times what the original material was for. So there has been a lot of push for things like this. So this is a device that you, pretty sure it's this one anyway, you dump all the fillets, you dump the pellets in, and then it melts it and extrudes it into a filament that then winds up. And there's been some really cool technology I've seen around that. Kind of reminds me of the Mr. Fusion engine from Back to the Future, where he builds the fusion engine to power the car, rather than plutonium. Anyway, neither here nor there. But basically, it's things where it's got a grinder and a melter and everything in it, and basically any plastic which has a thermal profile within the range, you can stuff in there and melt. So that includes things like milk bottles, various plastic packaging for electronics, whatever. You just get that all in there, you dump it out there, and it prints out usable plastic. So it's actually a new form of recycling. You don't actually have to go out and buy the plastic pellets at all. You finish your milk bottle, throw it in the machine, it'll munch it up, melt it down, and give you some 3D printing filament, which I think is pretty cool. So we're going to get onto this again in a minute, but complex shapes. So these guys, you see here, this is the actual robot that we scanned earlier, and if we print it, it has this big overhang. So in order to do that, it prints out this huge scaffold which attaches it to the side. So like we saw before on the MakerBot website, there's the MakerBot Replicator 2 and the MakerBot Replicator 2X. The main difference between the two of these, this has one extruder, this has two extruders. So two extruders allowed you to print in different colors and all this stuff, obviously, but it also allows you to print in different materials. So in order to make that into that, I had to get out a file and a penknife and carve it off very delicately and then file the results down. What you can do instead is you can print your scaffolding in a soluble material. So you print it in something which dissolves in a light acid or vinegar or something like that, and then once you've got that, you dump it in there and it'll dissolve away all the filament, which saves you a lot of time doing it. And resolution as well. So the MakerBot is a 100 micron Z resolution, so between layers, and we'll look at this again, but depending on how you print it, you end up with different different quality prints and so on and so forth. And future directions, I've already talked about quality. Prices always come down, so Peachy is a $100 3D printer. Materials, so printing in metals at room temperature, so obviously metals often have melting points in the thousands of degrees, but you know, they're getting them now so you can actually print it. So here's a little one which looks like it's made out of buckyballs or something, but it's not. Color, so you know, these ones are all printed out in one color with dual extruders. You can print out in two colors, but then there's the advantage of being able to print out in any colors. So this is one which, as it's melting the fabric, I believe the way this one works, as it's melting the fabric, it injects ink off an inkjet printer, so you can actually have things printed in different colors. We looked at the MakerBot Digitizer before, which is a 3D scanner, and scale. So, you know, they're more and more trying to shrink these things down. So here's a 285 micrometer race car, so that's pretty small. So that was just from a different presentation I gave a while ago, but we'll continue on with what we were doing, which is looking at 3D printing yourself. So obviously we need to, we've got our 3D model, so we've got, not that guy. We've got this guy here, which we've cut out of the, background. What's going on here? Yeah, it's just running incredibly slowly. I might have to reopen it. Yeah, so you don't have to use Mesh Mixer, but it's there.
Yeah, what's your one called? It's open source viewer. The other one you mentioned before. Oh, Mesh Mixer.
Oh, Open Scene Graph. So that's just for rendering. So Mesh Mixer actually allows us to actually modify the model as well, but there are plenty of other ones we can do. Okay, so let's say, okay, so we've got this. We've got a whole bunch of background stuff that I don't want. So let's start. Delete those. Delete that. Delete that. Oops. So let us. No, I don't. Go away. So now we've got more basic model. Let's jump into selection again, and now I'll just gently color around there. Depending on how keen you are, you can spend a very long time doing something like this. But that's about as patient as I am. Just get rid of these little chunks as well. Oops. All right, so there we go. We've got our dude standing there. He's more or less done. Sweet, let's 3D print it. Well, it's not quite that simple. So we have to make sure before we print our 3D model that it's suitable for printing, because geometry on a computer is represented by a series of positions in 3D space. It doesn't necessarily make it a good physical object. So things we've got to look out for is holes in the mesh. So Murray mentioned this before. If you have these objects in here are not treated as whole objects. So I could have a hole in the mesh, and in fact, if I go around underneath, you can see here we've got a hole in the mesh. We can see right up inside it. Technically, we could probably print that with a hole in the mesh and just print the outside of it, but it's going to be pretty flimsy. So that's not ideal. We don't want to have disconnected components. So you saw before we had all these bits floating off in space. You know, they're going to print out separately. The 3D printing software will do its best to sort of fix that, but it's not ideal. And we have what's known as non-manifold areas. So because these are things which are pull up the definition of a manifold, because these are just three numbers or like positions in 3D space, they don't have the idea of what's known as a manifold. So a manifold, in its simplest terms, we want to have a two-manifold 3D model to print. So that means that each edge in our 3D model connects to two faces, exactly two faces and no more. So we don't want two faces and then a third face sticking out. We don't want an edge with one face attached to it, and so on and so forth. The easiest way to think of it when we think about 3D printing, though, is we want to make sure that our model is watertight. So it wouldn't, if we filled up the inside with water, it wouldn't leak. And we want to make sure that there's no additional faces or edges. So the advantage to using Mesh Mixer, is we can use it to find non-compliant areas. So we open our model, and then we go down to Analysis, and then we can do our Inspector. And so we have a blue one. So a blue sphere is a hole. So this is treated as a hole because around the whole side of this is a non-manifold area. Each of these edges only connect to one thing. So what we can do is we can click on this, and it will repair our hole. So it's basically just filled in those gaps now. So it's one solid piece. If I load a more, import, replace. So if I load in this model, and for some reason I wanted to print everything, if I run my analysis over it now, you see we've got a whole bunch of stuff. So the red spheres are non-manifold areas, so that's non-manifold. It'll do its best to try and correct that, but it hasn't done it completely. There's a non-manifold area down there. Sometimes this takes a while depending on how complicated it is. We have magenta spheres, which are disconnected components, so this part isn't connected to anything which can print. There's a part down there as well. There's this little floaty bit hanging off the side. And then the blue spheres have holes in them, so we can repair all of these as well as best it can. Or we can just click on Auto Repair All, and it will do multiple passes to go through. So even after 10 passes, it wasn't able to repair all of that. So it's having some real trouble trying to fix some of these. In which case we might need to get into some manual intervention, but let's just say, again, doop, doop. And let's analyze it. Inspector, auto repair all. There we go. So from repairing it, we've ended up with this. Ignore, I don't know why that's reflecting light like that. I think it's just because it's kind of a concave thing. But, you know, nevertheless, we've got somewhat a 3D model. Let's just cut it off like we had before. Try and make a nice clean cut around there. Nice clean cut around there. The best quality model we can get. And analysis inspector, auto repair on. There we go. So this should now be more or less ready for 3D printing. So it's got a bit of a base and so on and so forth. Then we need to export it to what's known as STL file. So we go File, Export, and export that. And then we open our MakerWare software. So the MakerWare software you can grab off the MakerWare site. And the 3D printer we have here is a Replicator 2. So we open Robot New, and then it'll say, okay, well, the origin for this 3D model is actually in its chest, so it's done its best. It says it's off the platform, it's actually printed, so we go move to platform, and there we have our 3D model ready for printing, except it's going to be tiny, so we can resize it. If we just click on it, we can basically click and drag, or if we want to, we can double click on it again and specify things, turn off on or off uniform resizing, so on and so forth. We can rotate things, so we can rotate them around the Z-axis, not that that's really any use, or we can rotate them around various other axes as well, which can be more important, and which we'll look at in a moment. So when we're done with that, we're happy, it looks pretty good, click on Make, and then it brings up this thing. So if the replicator is plugged into your computer, you can click on Make It Now. The way we do it is we do it through SD cards. We go Export to File, Export for the Replicator 2, which is the one we have. What material we print out in PLA, so just leave that. And then you can specify the resolution. So normally it looks like that. You can open up advanced options. When you look at the layer height, 0.3 mil at low, 0.2 mil, and 0.1 mil. We have had problems printing at high resolution because the filament starts resticking to the nozzle. So usually we sort of try and print it at standard if you can.
Those French guys said
Okay, yeah, I mean, yeah, there's various things which need to be tweaked. Some of the filaments print better than others, I guess, due to the quality of it. So I found the green stuff prints quite well. The blue stuff used to, I haven't used it in a while, but some of the other colors don't print so well. You can modify the temperature. Recently I've actually been setting it to 235 degrees because I find making it a little bit hotter seems to stop it from sticking so much, but your results may vary. And you can, sorry? Yeah, so I've been printing at 235. Obviously if you go too hot, it's going to dribble out. If you make it not hot enough, it's just going to all stick up and fill up the extruder. So you have to be a little bit careful when you're playing with these settings, but 235 has been working pretty well, and the speed and so on and so forth. So yeah, usually use standard, temperature 235, leave speed settings, and we have rafts and supports. So scale the position, make sure it's on the platform. Give thought to how to position the objects on the platform. Overhanging parts will need scaffolding bits. Scaffolding bit which will have to be removed after to save plastic and printing time. So the less scaffolding you can have, the less plastic you need, and the less amount of time it takes to print. As a printer head does one layer at a time, depending on which way the object lays will determine how it looks. So I've lost one of my models, but I still have two. So you can see these are two different print orientations. So this one, he was facing feet down, so he's standing vertically on the print thing. And as it goes around, it prints up like this. So you can see, in this case, that's that one there. You can have a look at them. It prints sort of top to bottom, and it's looking quite smooth. And this one, which is this one here, I laid him down flat on his back, hoping that maybe I could save something on the scaffolding, because rather than having scaffold all the way up here, it would just scaffold from bottom to the top. but because that has printed from his back up this way now, it has quite a different texture on it and doesn't quite look as clean as the other one does. So have a look at the two of them side by side.
Do both things at the same time?
Sorry?
Do both things at the same time?
So it prints the material in between them as well. It's basically printing one big thing. Yeah, so if your model has any overhanging parts, which it probably will, you want to make sure that supports are on. So supports are the scaffolding basically, which holds it all together so it doesn't droop. Depending on how much overhang you get, you may or may not need supports, but it's usually the best idea to leave it on, because if you try and print something with too large an overhang with no supports, it will just fall off. And the other thing is raft. So this bit on the bottom is the raft. It's often a good idea to print the raft out as well, because it helps it stick to the platform. So if you don't print the raft, what we often find is the plastic will start sort of flexing up, because as it prints it and then it prints the next layer, as the next layer cools, it pulls a little bit. But if you print the raft to begin with, it gives it a large enough platform. So yeah, supports and rafts. We'll turn the lights on in a minute and you can have a look at it. But supports and rafts, so this is what the original one looks like, and this is the supports and rafts that go with it. And so when we're happy with all of that, we hit export. We want to SD print for version 7.0 or later, and we just save that, and you'll see it slices it. So this is creating basically instead of having a model, it's trying to create a series of, I guess, 3D chunks or voxels, or however you want to look at it, from a 2D model. Oh, sorry, 3D model. Yeah, that is by far the most tedious part of it, Yeah, you have to be really careful with that. So we slice it. That'll take a wee while, because it's basically trying to create a bunch of voxels. Verifies it to check that it's come up with a good thing, and then it will finally save it.
Like instead of getting the decoder, it's like giving the model, just sort of drawing the line and stuff.
Not that I'm aware of in the lab. Theoretically, you could do that, but
So, you said that's MakerBot 2.
no, that's the MakerBot 2X. Just to make it confusing. So 2 is the model number, and then the X means that it has dual extruder. Yeah. So, and there are other ways of smoothing it as well. So you see there, it's quite rough. You can either sand it down. Various people have had success, like using various acetone-based things like nail polish and stuff to sort of smooth off the edges and stuff like that. But anyway, so we've 3D printed that now. We have somewhere on our desktop robotnew.x3g, and we go and grab the SD card out of the printer, copy that on there, put it back in the printer, and then on the little menu screen you go to build from SD card, select it, hit build, come back in 40 minutes. It'll be done. If we were doing a homework assignment, I'd get you guys to print something, but you can do that in your own time. You're welcome to use the 3D printer, although if it's for non-work related stuff, we ask that you pay for the filament that you use. So I think that's pretty fair. The filament isn't actually that expensive, and there's a little scale in there you just weigh to determine how much it is. So last stretch, applications of 3D printers. So one of the first things, one of the first sort of things that everyone was printing because they could were these whistles. They're printed with the little, what do they call it, the bead or whatever in there. You just reach in and snap it off, and then you have a working whistle. Brilliant. 3D flexible grids. So there's what's known as the grasshopper definition, which prints things, and it prints it in such a way that you have all these little hoops and stuff, and you can print various flexible grids for making stuff which are flexible. Plenty of stuff on there. The material itself is rigid, but the way they join with little hoops and catches, that allows you to flex it. So the material is flexible. The material is rigid, but the structure is flexible, which leads into things like fabrics, fashion, so on and so forth. You can do some quite crazy stuff. 3D printed characters, obviously. So I think Shapeways does stuff like that, or there's various websites anyway. You can send in a photo of yourself and they'll print you out a little 3D cake topper. You could even get it printed in cake frosting so you could eat it. Brilliant. Zeotropes, you know, it was just an interesting little application. So the zeotropes are basically like a whole bunch of different things, and you shine a light on them at the right time, and because of persistence of vision, zeotropes. No, how do I spell it? That is correct. Pretty sure they're called zeotropes anyway. Doesn't seem to be relevant, but yeah. Oh, there we go. This one here. Pretty much. Yeah, so this is just a nice little thing tied in with an Arduino, just to basically, it has a little light sensor, which you see it's got this black and white grid in here, and the black and white, when it detects it's on a white part, it turns the light off. And then when you look at it, you see a little man marching, but in reality, it's just from persistence of vision, because the lights are turning off in between parts and then lighting up. Your eye can only see the parts when it's light, so it looks like it's marching. It's kind of a cool little thing, and that was all 3D printed. The guy made a 3D model of an animation of a 3D model walking, and then just printed it all out on a sphere. It's pretty cool. 3D printed lamps, 3D printed guitar bodies, so you can pay someone to generate your own 3D printed guitar body if you're so inclined, and so on and so forth. So obviously not everyone has a 3D printer, not everyone's a 3D modeler and stuff like that, so this basically boomed this new online service industry. So you have things like Thingiverse. So the same people who did MakerBot realized that not everyone has 3D printers or the skills to do so, and so they created what's known as Thingiverse.
That'd be expensive.
Yeah, it's more expensive than printing it yourself, but it's, if you only need one or two things, it's less expensive than buying a 3D printer. So, you know, so they're running a contest right now to do T-Rex remix. So you download a T-Rex skeleton, or skull rather, and then you can 3D print it. So these are all the various contest entries people have put in. So a GoPro case, finger puppets, shower heads, tea towel holders, clothes pegs, door handles, you know. But you can download all these models, print them out yourself, or you can ask people to, or pay for people to print them for you, so on and so forth. So you can go on here and download various bits and pieces. So yeah, and it's, you know, Thingiverse tries to sell itself as a wiki of things. So obviously we have the commons repositories. We have Wikipedia, which is knowledge, YouTube, which is information, entertainment, and Thingiverse, which is things. It's user-generated consolidation, codification of knowledge, reduces duplication of effort, non-restrictive nature, maximizes value creation, so forth. So, you know, you can download all these things. One of our master's students built this last year, turbine rotary tool. So you push air in it, and then it spins a little thing at up to 6,000 revs per minute. It's kind of cool. Various other things, whatever. There's things which are slightly more useful than others. So if you've got these old wooden track sets from when you're a little kid and you lose a piece, there's things on there. So if we copy and paste this, so you can print out your own track pieces. So if you've lost a piece, you don't have to go out and buy a new one. You can just 3D print it. Whoops. Too many things open. Yeah. Various other things. So the Geneva wheel, which is kind of a cool little thing, which turns rotational motion into 90-degree sporadic motion. Nuts and bolts, ducted fans, glasses, ball bearings, ergonomic handles, clips. I recently printed out, I should have brought one with me actually, I have the super tub in my laundry, you know, the big tubs that you wash stuff in, has like little plastic handles on it, and then the plastic handles underneath them, they have like a little metal toothed gear which connects to the actual pipe, and the plastic handle mates with the metal thing by a little plastic insert, except those plastic inserts get stripped off. So I modeled one up in Google SketchUp, or whoever owns it now, Garmin, one of the 3D modeling companies, the 3D GIS companies anyway, and modeled it up, 3D printed it out and replaced it, which was quite good because you can't actually buy those little inserts. As far as I can tell, I went around a few shops, you can only buy the whole tap piece, which costs $40, and it cost me about 40 cents in 3D printing plastic to print out my own ones. They're not as strong as what you would buy because those ones are injection molded, but it works. So yeah. There's other things. There's other things as well, so you can 3D print parts for your own thing. So this one, I believe, is for the parts which attach the extruder to basically the rest of it. So these parts up here, there's a bunch of stuff someone's 3D printed, so you can, if your thing breaks, you can repair it. Although if it's broken, then you can't print them, so you can't actually do it, so you have to print them beforehand. So it becomes this big thing. Autodesk has their own one, so Autodesk, we've been using their tools. They got a bunch of stuff you can print out. Google has a 3D warehouse for various things you can download and print out as well. So those are sort of commons repositories. From there was other people to bring digital desktop fabrication to the masses. So there's things like Shapeways and Pinocchio, which work to basically provide services. So you can, on their website, you can design, buy, and sell custom products. So if you make something you think is really cool, you know, so you guys want to do your own zeotropes. So there's someone who's built those wind walking machines, I guess. But you can go on there and, let's say I'm really desperate for a jellyfish lampshade. I can pay $600 and they will print it for me. Well, I mean, if you were to go buy that from a professional thing, it would probably cost the same amount. A webcam privacy screen if you're worried the NSA is watching you. Oh, well, I mean, they can, but I don't think I'm doing anything which the NSA would really be that interested in watching. Yeah, pretty much. Egg cups and so on. But yeah, basically, you know, you can create your own stuff, you can upload it, you can sell it, you can buy it, and they'll 3D print it for you, and so on and so forth. Pinocchio, pretty much the same deal. Laser cutting, 3D printing, made easy. You make your own stuff, buy, sell, whatever. Buy, sell, make, whatever. So there's all these services which now do stuff for you if you really can't be bothered. So in 3D printing and other things, so 3D Pinocchio does laser cutting as well, so you could laser cut, get your own rocking horse laser cut, whatever. And there's lots of other ones as well. iMaterialize, which is a Belgium service, Sculptio, which is French, so everyone's doing their own stuff. Then there's the idea of co-creation as well. So say you want to do a customized vase or something, lampshade maybe, but you want to make it as a gift, you want someone else's name on it rather than just random words. Like a lot of these offer these co-creation interfaces, so either automatically or through you know, services offered by people. You basically, you know, for this one you can imagine you type in some text and it will use an algorithm to basically create the text, or it might be a case that you send in a sketch and somebody makes a 3D model of it for you. So if you're not good at 3D modeling or you want to do some customization, whatever, you can have these 3D models created for you to print yourself, or you can get them, you basically submit what you want and they will create it, print it and everything yourself. And moving on to sort of the last thing is the idea of fab labs. So fab labs are fabrication labs, and this is sort of taking the idea of community and bringing it from the internet into the real world. So fab labs are basically spaces where, or they're sometimes called maker labs and stuff like that as well, where people get together and they pool, or they get some money from various companies through sponsorship or whatever, or you know, people pool resources or whatever and basically put all these things together so that if you don't have a 3D printer, you can go in there. Sometimes they charge you a small fee for using it or a subscription, sometimes it's free. But basically you go in there and there's experts and stuff like that who will show you how to use the materials and all that sort of stuff. And they have things like laser cutters, CNC mills, vinyl cutters, 3D scanners, electronics, CNC mills, digital sewing, 3D printing, all sorts of stuff. So, you know, it's basically a space where you don't have to buy all these things yourself. You can go in and for a subscription or a small fee or whatever, you can use these things to do the stuff you want to do. So fab labs are sort of a movement or whatever, and they have a set of rules that, you know, in order to be a fab lab you have to adhere to. So you have to support public access, so the public can use it, can't be private. You have to support and subscribe to the Fab Lab Charter. You have to share a common set of tools and processes, so you have to provide tools and ways of doing stuff. And you have to participate in the global Fab Lab network, so you can't be an isolated entity. You have to sort of feed back into the community. And they have a conformity rating, which the code describes how closely a lab meets the condition of the Fab Lab label. So there's the FabM, which is a yearly meeting for Fab Labs. This is quite old now. There was one in New Zealand. It was probably a couple of years ago now, but you can sort of see where these things are. And there's the International Fab Lab Association, which basically defines the rules and all sorts of stuff. So these can be as advanced or as simple as possible. So there's a Fab Lab in Amsterdam, in this really cool old castle. Fab Lab in Afghanistan. Yeah. So, I mean, you know, it's not just limited to sort of USA and Europe and stuff like that. They could print their own bulletproof armor, maybe. There's mobile Fab Labs, so these are basically set up in trailers and drive around. In Christchurch, we have the MakerCrate, which is a Fab Lab in a shipping container, because that's how we roll in Christchurch. We just stick everything in shipping containers now. And hackspaces and makerspaces, pretty much the same sort of idea, and there's lots of them around. Wellington has a makerspace you can go and have a look at. Oh, and there's also, I actually added a couple of slides which I forgot to copy over. There's the Christchurch has the MakerCrate. Unfortunately, if we go, I think MakerCrate's their website. I found their website to be a little bit underwhelming, I guess. Doesn't really have a huge amount of information or anything on there. So this is their official website. Their goal is to design and build a makerspace for under $15,000 US or less. So they're basically, they've tried to create this thing and then provide the information to the public. So, you know, anywhere around the world, like a bunch of people could get together, raise some money, $15,000, and build their own thing. Yeah, it's a couple of years old now. So there's actually not a huge amount of information on here, which is bit of a pain, but they do actually have, if you go to meetup.com and search MakerCrate Christchurch, there is Christchurch MakerCrate, and it's quite good. They have meetups where so there's 187 people subscribed. They've had 24 past meetups, but so April the 12th, which I guess has already been and gone, they had a session on intro to 3D printing. They have mini makers. They have all these sessions you can go to for, I think, a minor fee. So I think I had a look at one of these. So there was an introduction to 3D printing, $25 per person, 2 hours, maximum of 5 people, and they teach you how to do stuff like 3D printing and all that sort of stuff. And you know, so they're sort of trying to get out there. And the MakerCrate is up and running. You can contact these guys. I've got a few friends who are pretty heavily involved in this sort of stuff, and you know, they're out there to try and help people, to encourage people to be creative and to learn how to do these things. They had there was a TEDx in Christchurch last year, and there's going to be another one this year. Actually, I was contacted by the organisers asking the HITLab if the HITLab would be interested in helping out again. We did last year, and they had the MakerCrate there with all sorts of stuff going and handing out brochures and stuff like that to try and get people involved and interested, because, I mean, these things are community driven, so they're not really getting paid to do it. These are people who do it for the passion, the interest, and all that sort of stuff. That's it. We're done. So yeah, Mark will be taking a lecture tomorrow, I assume. I'll double check with him and get him to email you guys to let you know. Otherwise, that's pretty much all the material I had to cover. I will still be around the lab, obviously, if you guys have any questions or anything. But otherwise, go forth and do your thing.
The plastic prints and like in the industrial, how they do, how they print the stuff, what do they use? So
they usually use things like injection molding. So what they will do is they will create a mold of it, and then they just pump the plastic in there, and then they shake it and they heat it up and so on and so forth to get rid of all the bubbles and imperfections. There has been efforts made to do injection molding.
They make bottles that way.
Yeah. So yeah, there's that way. I can't remember what that's called, but so there's that way where you have the mold and you heat it up and then you use a vacuum to suck it off. There's injection molding as well, where you basically create. In fact, here's a sort of thing here. You create a mold and then you inject a plastic into it, and when it cures, it takes the thing off the mold. 3D printing and stuff is not really designed for sort of high runs. Making the molds and stuff can be quite expensive, so on and so forth. That's why it's usually very late in the sort of production process that you start doing that, whereas what we're trying to cover in this course is more prototyping. But there have been people who do so 3D printed plastic injection molds. So you print out a 3D mold and you get something like one of these and you sand it down, you clean it up, make it as nice as you can, and then you stick it, you basically make a plaster mold of it, and then you cut out the mold and then you just inject the plastic into the mold. And you can do, like, you can imagine if you had a block of plaster and, you know, in it you made molds of, say, this guy. So you got this guy, got some plaster, put him in there, sealed it all up, and then cut it off gently, took him out, and then made multiple molds. You could have like a dozen things, and then you just go through, fill them all up with plastic, and you're mass producing them, sort of thing. And it's generally faster, but there's a lot more. Like once the mold's made, it's made.
Yeah.
You know, you have to, if you want to make any changes to it, you have to go back and remake the entire molds and stuff like that. So, you know, the sort of stuff we're teaching you guys is to get to this level, to get from here to the next stage, which is mass production. You know, there are various, mold making is usually the way they do it.
Cake molds are interesting to watch. Like the thick plastic sleeve like that. The mold closes like that with the plastic sleeve and they blow air into it.
Yeah. Yeah, so there's a bunch of additional stuff because you want to inject the plastic in there. Obviously, you don't want there to be any bubbles or anything forming inside the plastic. So sometimes they use vibration and stuff to shake the mold gently and try and work all the bubbles all the way out. But yeah, that's roughly how they do it. I'm sure different things have different ways, but usually it comes down to the fact that they have a mold so they can make thousands and thousands of copies of it. One interesting thing actually, who was it? I don't know if any of you guys watch Top Gear or are into car racing or anything, but Koenigsegg recently actually released, so they have, Koenigsegg is I can't remember, some sort of European car manufacturer who make like really ridiculously fast cars, but they recently published some article where they talk about how they 3D print a lot of their components while they're prototyping. See if I go to, pretty sure I saw the article on Hackaday. But yeah, they do things like, for example, when they're designing their chairs, they make a rough model of the chair and then they 3D print out components so they can sort of fit it to the human body. And then once they've got a nice fit, they, I'm not going to be able to spell this. They, make a mold of it. Oh, here we go. So this is the guy basically, you know, holding a 3D printed mold of part of something. So Swedish car manufacturer, so they 3D print it, then they laser scan it and modify it so that way they can make adjustments to the mold. I guess they could, you know, add on bits of plaster and stuff like that. And then they machine stuff from aluminium. And there was, so there's, yeah, a talk where they're talking about, but I think they look at somewhere in here, or somewhere I saw that they talk about stuff to do with, like they do various things like parts of the steering wheel, the brake levers, all that sort of stuff, so they can test them out and see, you know, 3D built this time. So built a turbocharger for it, like prototype it out on a 3D printer. So, you know, these are actually being used out in industry as well for the prototyping stage. Obviously, you wouldn't build a turbo out of 3D printed components because it would explode pretty quickly, but you know, for printing out the bits and pieces and making sure that it fits nicely, you can do that. And there are air turbines and stuff you can build on the 3D printer.
Thank you very much. Yes.
Thanks for all the classes.
That's right. No worries. And yeah, as I said, I'll follow up with Mark and check whether you guys are having a lecture tomorrow or whether you guys get the day off. You can have a play with the 3D printer.
Yeah.
Although you have to just check with the French guys because they're printing out a robot for Christophe at the moment. So, and unfortunately, the French guys have been hanging around.
Oh, right. Are they French, are they?
Yep.